All right, so towards the end of our last class, we had developed a full equivalent circuit model for an induction motor. So this is just kind of a recap of what we were doing. So our full model looks something like this. Here were our terminals of our motor, across which we control this voltage V1. We have our stator resistance, which I'm going to call R1, our stator reactance, JX1, then we had our core resistance, R sub C, and our magnetism reactance, JXM, like so. Once again, this dashed red line here is going to represent, or I guess it's not red, I clicked the wrong thing, but either way, this is representing our air gap. And then on the other side of our air gap is our stator referred equivalent circuit for our rotor, where this is going to be JX2 prime in series with a resistance of R2 prime. This R2 prime is representing our copper losses. And then we have an R2 prime over S times a factor of 1 minus S, representing, I believe, our mechanical losses. And this whole thing is operating at a frequency of our stator frequency. Just for what it's worth, this is our current I1. This is going to be our current I2 prime, so that is our rotor current for what we're working on. And let's leave this there. So this is the IEEE model. Or actually, this isn't the IEEE model. The IEEE model we got by simply eliminating that, what you call it, core resistance, so that we would just have a JXM here, right? So let me just put a note here. So this is the IEEE model. And then we essentially simplified the IEEE model to some extent by using Thevenin and Norton equivalent current circuits, right? And so that particular model would look something like this, where we had our Thevenin voltage here, our Thevenin resistance, our Thevenin reactance, this is our dash line for our air gap. Our rotor reactance. And this is just our total rotor resistance, where this current is I2 prime, our rotor current, and this current I1 is our stator current. And just for the sake of argument, just real quick, like what we found for this Thevenin model, and let me label this guy real quick, was that our Thevenin voltage magnitude would be the magnitude of V1 times XM over the square root of R1 squared plus X1 plus XM quantity squared. All of that is underneath the square root sign, and this could be approximated as the magnitude of V1 times XM over X1 plus XM. Our Thevenin impedance Zthev will be equal to JXM times R1 plus JX1 all over R1 plus JX1 plus XM, and that can be approximated as R1 times XM over X1 plus XM quantity squared plus JX1, and our current I2 prime's magnitude would be the magnitude of our Thevenin voltage divided by the square root of R Thev plus R2 prime over S quantity squared plus X Thev plus X2 prime quantity squared. So these are a recap of the relationships that we got. And then after we did this, we went through and we just simply used some of these results to calculate air gap power. And then that was kind of where we stopped. Okay. So here's our Thevenin model. These are the parameters for the various things. All right. So just to recap that air gap power really quickly before we move along to the new relationships. So PAG was 3 times the magnitude of our rotor current squared times R2 prime over S. And this came out to be 3 times the magnitude of our Thevenin voltage squared times R2 prime over S divided by R Thev plus R2 prime over S quantity squared plus X Thev plus X2 prime quantity squared. All right, so this is where we'd stopped at the end of the last class meeting. So the only thing that we didn't really talk about at the end of the last class meeting was how to use these relationships to get our equation for torque and things like that. So that's where we're going to talk about right here. And that's the last little topic that I want to talk about before we just start working out some problems and stuff. Okay. So let's start with the torque developed across the air gap, okay? So that's our mechanical torque being applied to our rotor. And that quantity is literally nothing more than our air gap power divided by our stator angular frequency. And so we're literally just going to take that equation for our air gap power, and then in the denominator, we're going to have a factor of omega s. Nothing particularly wild or crazy there. So that would look like 3 times the magnitude of the Thevenin voltage, quantity squared, times R2 over S divided by omega s times that quantity R Thev plus R2 over S squared plus X Thev plus X2 prime squared. So this is our torque relationship as a function of slip, right? So it depends on S. So what I'm interested in now is effectively using this torque relationship to figure out a couple of different things. One that we might be interested in is the torque that the motor would be able to produce at startup. So at startup, what's the slip? Let's start there. Anybody have any thoughts? If it's 1 or 100%. So at startup, our slip will be 100%. Can you explain why, Zach?
Well, there's no movement happening at startups.
Exactly right. So the slip is the difference between the synchronous speed and the rotor's actual speed. And if the rotor isn't moving, then the slip is 100%. Okay, so 100% correct there. Good job. So at startup, S is equal to 1. And from this, we could say that our startup torque, so T start, is just going to be 3 times our magnitude of our Thevenin voltage squared times R2 prime over omega s times R Thevenin plus R2 prime quantity squared plus X Thevenin plus X2 prime quantity squared, like so. So our S's went away because our slip is 1. Okay. Nothing wild or crazy there. Okay. Now, as I mentioned a couple of moments ago, the torque that is developed is dependent on slip. So there will be some specific value of slip that is going to generate the maximum amount of torque. I'm not going to make you guys suffer through that math, but how do you find the maximum value of a function? Take the derivative and set it equal to 0. Absolutely right. So to find the slip, at which maximum torque is developed, we can take the derivative of Tmech or our air gap power. And I'm saying that because those two quantities are just related to each other by a constant, which is just the inverse of our synchronous angular frequency. So either way, we're going to get the exact same result and set it equal to 0. So essentially, our maximum slip, or excuse me, the slip that generates the maximum torque can be found by taking the derivative of our air gap power as a function of slip with respect to slip and setting that equal to 0. And if we do that, we find that our air gap power, sorry, that should be AG, occurs when R2 prime over S is equal to the square root of R Thevenin squared plus X Thevenin minus X2 prime quantity squared. So if we substitute that relationship in to find our slip, that becomes simply R2 prime over the square root of R Thevenin squared plus X Thev plus X2 prime squared, all of that under the square root. And lastly, our maximum developed torque is then 3 times the magnitude of our Thevenin voltage squared over twice omega s R Thev plus the square root of R Thev squared plus X Thev plus X2 prime squared. Okay, so this is the last bit of material. And now all I want to do with the rest of our class meeting is work examples showing us how we're going to use these things. So before we get into that, mention at the beginning of class because somebody asked, we are going to have a test next Tuesday. Okay, so the test is going to cover electromechanical energy conversion as well as induction motors. That is it. So that would be homework 5, 6, and 7. All of them have been posted to Canvas. Homework 5, which I posted, I think last Thursday, is due tomorrow. Fairly brief, it's only 2 questions, okay? So you've had 4 days to do it. You are gonna wait until the day to do it any damn way. That's neither here nor there, but you've still got, I think, time to get that done. I believe it's due tomorrow. If it's not due tomorrow, I can make it due tomorrow. Okay. Then there is a brief homework set related to essentially just like the slip relationships and all of that kind of good stuff, number of poles, things like that. That's due Friday at midnight to give you guys plenty of time to do it. Again, only 3 problems. Realistically, that whole homework set right there should probably take less than an hour. And then lastly, there is a final homework set over this material that we just covered using the equivalent circuit and all of that kind of jazz. We're going to work some problems on that. That is 2 problems long, and it will be due next Tuesday so that you turn it in. Realistically, you should do it before you take your test and all of that kind of good stuff, okay? I also intend to work some example problems out just from various textbooks, upload my solutions so that you guys can use those as practice for things as well. That being said, the example problem that I want to work today has 12 parts so that you literally have an example of how to calculate pretty much anything I could ever ask you. Okay, so that is the reason why it is 12 parts long. So let's get into that horrifying thing. Yes. Yes, you may bring your homeworks with you as and an equation sheet for the exam next Tuesday, the exact same parameters as you had for exam 1. Yes. I believe so. I haven't graded the take-home portion yet, but I can tell you that a lot of you guys made a lot of really simple mistakes on the in-class portion of exam 1, and so the take-home portion will probably be the thing that saves your grades. Haven't looked at the take-home portions yet, so I'm just making a broad assumption there But not trying to be too much of a dick, but area of the circle isn't that hard to calculate.
Look, we didn't expect a circle, okay? Didn't compare.
That was first day of class. Circle threw me for a loop.
Yeah, I was like, wait.
I mean, you guys ostensibly, no, I'm not gonna, that's insulting. I'm just gonna stop and just,
Geometry or tricks in high school,
We are
okay?
dumb.
We may be slightly dumb. But.
I feel very strongly.
Higher layer.
There you go.
Man.
May have calculated the radius right, don't know. Anyway, neither here nor there, but
We got the pirate card, that's all we had.
all right, so here is our giant example.
How giant.
I literally told you it's 12 parts. So what we have, a 3-phase, 2-pole, 35 horsepower, 60 hertz induction motor. Is connected to a 480 277 voltage source. So before we even move along from this part right here, what does that 480 277 thing mean? Anybody remember that? So that's a voltage source. So it's not a transformer or anything like that. So that's not a primary and a secondary. So the 480 would be what you would have if you had a delta connection, and the 277 would be the voltage that you would see with a Y connection, right? So 480 would be line to line, 277 would be line to neutral. The reason why I am bringing that up very specifically is because you got your hand raised. What's up? The letter Y. So the reason why I am bringing that up is because the equivalent circuit model that we developed was similar to the single phase equivalent circuits that we dealt with way back in 280, where we were looking at essentially what was going on each phase for a Y connection, okay? So if our equivalent circuit model for our induction motor is making the assumption that we are dealing with a Y connection, which of those two voltages should we use? The 277, the one that represents the Y connected voltage. Okay, so I just want to be real clear and upfront about that. All right. So the motor has the following constants per phase. Referred to the stator. So we're going to have a resistance of R1. So this is our stator winding resistance of 0.322 ohms. We are going to have X1 is equal to 0.675 ohms. R2 prime will be 0.196 ohms. X2 prime will be 0.510 ohms. And our magnetizing reactance will be 12.5 ohms. Okay. The total rotational losses are 1,850 watts. And are assumed to be constant. And then here's the information. So for a rotor slip of S is equal to 3% at rated voltage and frequency, determine the following quantities. And we'll just go through these one by one. Okay. So the first thing that I want us to find is the synchronous speed ns and the rotor speed nm. So anybody have any thoughts on how we might determine either of those things? So the synchronous speed is going to be the speed at which the stator field is spinning, which will be directly related to what's going on, like the applied voltage source. Yes.
20 FS over P.
Okay. So
FS is our hertz.
NS is 120 FS over P.
Oh,
Okay.
wait. NS should just be the RPM, which is 3,600.
So it will come out to be 3,600, absolutely. So if we do 120 times 60 over 2, that is 60 times 60, which is 3,600 RPM. 100% correct. And you should get to a point essentially where if you have a 60 hertz motor and it's 2 poles, you know synchronous speed is 3,600, 4 poles is 1,800, et cetera, et cetera. We already talked about that. That is one of the homework problems that you're going to do is literally fill out a table that tells you what the synchronous speed is going to be for various number poles here in the United States where we have 60 hertz and over in Europe where you have 50 hertz. But yes, this is the math behind it, or you could have looked at the damn thing and said, oh, hey, it's 3,600 because it's been 3,600 every time we had a 2-pole motor at 60 hertz. Either way works for me. So knowing our synchronous speed, how do we then get our rotor speed?
VNS times 1 minus S.
Exactly right. So Nm is simply Ns times 1 minus S. So that would be 3,600 RPM times 1 minus 0.03. And this comes out to be 3,492 RPM. So before we move on from this calculation, everybody okay? Yes. A 2-pole, yep. I have to tell you, so I told you in the problem statement. Fair, very fair, but yeah.
If I don't see a pole, I'm assuming it's 2.
Assuming 0.
There's 0. There's no
There-
motor. There's no motor.
Yeah, it's a 0 pole means no motor, yeah,
No
so.
motor, so no problem needs to be solved. It's just a
Yep.
block of a block of steel.
All right. Jackassery aside, let's move on to the next thing. We have 11 more parts to do. Okay, so the next thing that I want us to find is the rotor current. What?
Remembering that, what did you say? That no pole, no motor?
No. So I want us to find the rotor current I2 prime. And I'm really only interested in the magnitude for what it's worth. Okay. So, yeah, we're trying to find the magnitude of I2 prime. Okay. So, if we go back up to our recap from earlier today, all we're going to be doing is applying this equation right here. However, this equation right here has several constituent subparts that we also essentially need to figure out. Okay.
Where we can find the Thevenin.
Okay. So we could find V Thevenin. And we really only need the magnitude of V Thevenin, right? So the magnitude of V Thevenin. And let's use our approximations here just so that we don't have a ridiculous amount of math to do. Is going to be the magnitude of V1 times XM over X1 plus XM. So what is our magnitude of our applied voltage that we're going to use here? 277, because our equivalent circuit is a Y-connected equivalent circuit. So 277 volts RMS. XM was 12.5 ohms. X1 was 0.675 ohms. And then we have that 12.5 ohms yet again. And I got 262.808 volts RMS. Okay. So going back to our equation, just really quickly here. So we got the magnitude of VThev. So great, we got the numerator done. Now we need to figure out all of that other stuff, right? So the other thing that we would need specifically would be RThev and XThev. So looking at this expression for ZThev up above, which part is RThev?
Or no, it's
This guy right here. The real part of our Thevenin impedance is the Thevenin resistance. The imaginary part of our Thevenin impedance is the Thevenin reactance. Okay. So RThev is going to be R1 times XM over X1 plus XM quantity squared. So that would be 0.322 ohms multiplied by 12.5 ohms over 0.675 ohms plus 12.5 ohms squared is 0.290 ohms. And XThev, from what we just looked at a moment ago, is literally just X1. So this comes out to be 0.675 ohms. So the magnitude of our rotor current is the magnitude of our Thevenin voltage divided by the square root of RThev plus R2 prime over S plus, sorry, and that should be quantity squared, XThev plus X2 prime quantity squared. All of this goes underneath the square root sign. And now we'll start putting in numbers. So the VThev is just the 262.808 volts RMS. Then we're gonna have the square root of 0.290. R2 prime, if I scroll back up here, was 0.196 over my slip of 3%. So that's going to be 0.0, sorry, I put too many zeros there, 0.03. So that's my first term, square that guy. Then I have my x dev, which is just x1, so 0.675 ohms, plus my x2 prime, scroll up for that guy, that was 0.510 ohms. Square that thing. Once again, all of this goes underneath a square root. And when I calculated this, I got 37.948 amps RMS. All right, so how did we feel about that guy? A little tedious for sure, but just simple and direct application of things. So the next thing that I want us to find is going to be our stator current, and that'll be a little bit more involved. So our stator current is going to be I1. And once again, let's just really concern ourselves with our magnitude. So I want to scroll up and look at our equivalent circuit models that we have here, okay? So what was that? Yes. And that's what we just found. Okay. Actually, so I have a little bit of a mistake right here. I'm going to erase this guy. The reason why that's not going to be our rotor current is I2 prime, our stator current is I1. The reason why that I erased that current right there is I just erroneously drew it on. So our our stator current is this guy right here, which that's a terrible color choice. This guy right here. Now, that is the current that is effectively leaving our voltage supply, okay? So I think probably the easiest way to find this particular guy would be to find the equivalent impedance of the motor itself, and then simply divide the voltage that we apply across the motor with the impedance to give us our current. Okay. So that is the approach that I am going to take. So how would we find the impedance of our motor? So let's look back up here, and we're using our IEEE model here, okay? So anybody have any thoughts on what that might be?
the green was stator side and green JXM, so.
I just want impedance. So that's the rotor. Is that the whole thing? The whole thing. So I think Brock's got it there. So I would take effectively this impedance, which is my rotor, put it in parallel with JXM. And then to that, I'm going to add my stator impedance because that's in series. Okay. So R1 plus JX1 and then plus JXM in parallel with this guy over here, which Nick was correct about in saying that we could simplify that R2 in series with R2 over S times 1 minus S. That's literally just R2 over S. Okay. So our motor impedance would be R1 plus JX1. So that's our stator. Then we have our core in parallel with our rotor. So that's going to look like JXM times R2 prime over S plus JX2 prime all over R2 prime over S plus JXM plus X2 prime, based on the IEEE equivalent circuit model. Okay. So if I've subbed numbers into here, I would have 0.322 plus J 0.675 ohms plus J 12.5 ohms times 0.196 over 0.03 plus J 0.510. And then down here in my denominator, I'll have that 0.196 over 0.03 plus J, and then this will be 12.5 plus 0.510. And I wound up getting my motor's entire impedance to be 265 with an angle of 34.893 degrees. Oops. So from this, how would I find the magnitude of my stator current? Yeah, 100%. So I could find the stator current itself by just taking the voltage and dividing by the impedance. Because I'm only interested in the magnitude, I'm going to be slightly lazier. So by that I mean my magnitude should just be the magnitude of my voltage divided by the magnitude of my impedance, and that will give me the magnitude of my current, which is what I'm interested in. So that would look like 277 volts RMS divided by 6.265 ohms. And I get 44.214 amps RMS. So to be very, very clear here, the reason why I wanted to make sure that I use the IEEE model is because I didn't want to accidentally neglect the fact that a pretty significant amount of my input current or my stator current is going to wind up getting leached off and will flow through that core and magnetizing reactance. Not all of it flows down through the rotor, which is what our Thevenin equivalent circuit makes it look like is happening. So that's specifically why I wanted to make sure that we used the IEEE equivalent circuit model there. All right. So scroll back down here. Everybody okay with the calculations that we've made to determine our stator current? Any questions, comments, or concerns for there? I know this is dry and boring. I want to make sure that you guys can do it so that when it comes time for your test next week and doing your homeworks, you have an understanding of what the hell it is I'm asking you to do so that it is, let's say, mildly less of a train wreck.
Well, that's on the in-class assignment, or in-class goal. What's the areas?
Maybe. That's a genuine maybe. Okay, so again, we're devolving into jackassery. We've only got an hour left and we've got 9 more parts of this thing to do. All right, so part D. At what power factor does the motor operate? Okay. So, anybody have any thoughts on this guy specifically? So there's multiple different ways that we could figure this out. The easiest way is, for lack of a better word, a little bit of a deep cut from 280, okay? So just to recap a couple of things, I'll do this in orange. This isn't part of the calculation. I'm just trying to remember, to help you guys remember things. So power factor was defined in a couple of different ways. It was the ratio of the average power to the apparent power. We don't have either of those quantities. Or it was the cosine of our power factor angle, theta S. Well, theta S is simply the difference between the angle of the phasor voltage V and the phasor current I, which is literally the exact same thing as the angle of the impedance of whatever we're looking at. And wouldn't you know it, in our last step, we calculated the impedance. So our power factor should literally just be, let me write this as PF motor, the cosine of the angle of our motor's impedance. So that would be the cosine of what angle? Let me scroll up for you guys.
34.8.
So 34.893 degrees, okay? So when I put that into my calculator, I got 0.820. Is this lagging is indeed correct? Tell everybody why, Zach. Because it is a positive angle. Absolutely right. Positive angles mean lagging power factor, negative angles mean leading power factor. For what it's worth, in an induction motor, it's always going to be a lagging power factor. When we get to synchronous machines, it could be either leading or lagging, depending on how it's connected and all that kind of good stuff. All right, so part 4 done. This was a review of stuff that we've done previously, so let's keep on trucking. Now I want us to find our air gap power. So this is just another application of an equation that we covered last week, and I reminded you all of what it was earlier today. So I'm literally just going to write this equation down. 3 times the magnitude of our Thevenin voltage, which we already determined in a previous step, squared, times R2 prime over S, all divided by R Thev plus R2 prime over S quantity squared plus X Thev plus X2 prime squared. All of these things at this point are known to us, so we can simply put in our numbers. So 3 times 262.808 volts RMS, square that guy, 0.196 ohms over 0.03, that's my R2 over S, all over 0.290 plus 0.196 over 0.03, square that guy, 0.675 plus 0.510, square that guy, and this comes out to be 28.225 kilowatts. So that is our air gap power, just direct application of our equation. So now, knowing the air gap power, how might we find the mechanical power Pmet? It is indeed. Exactly right. So just our mechanical power Pmech is just our air gap power times 1 minus our slip. So that is 28.225 kilowatts times 1 minus 0.03, or 97%. And that comes out to be 27.328 kilowatts. Okay. Now, let's find the output power delivered to our shaft. So this one is going to be a little bit more involved. And it comes from that power flow diagram that I showed you guys. So I'll remind you simply that our shaft power, P shaft, would be our input power, P in, and then we would just wind up subtracting our losses. Okay, well, we already have our rotational loss is quantified, right? And we're also told, I believe, that so our rotational loss is our stray losses, our friction and windage losses, as well as our core losses, all lumped together, if I'm remembering correctly from our last lecture. So the only other losses that we would need to take into account would be the copper losses in our stator and the copper losses in our rotor. So I'm just going to put minus P1 comma CU representing the copper losses in our stator, and P2 comma CU representing the copper losses in our rotor. And I'm going to give us some space to where we can put those numbers in, but now we need to figure out those constituent parts. So let's start with our input power. Anybody have any thoughts on that guy? So our complex power at the input would be the voltage drop across our motor squared divided by the complex conjugate of our motor impedance. That is definitely one way that we could do it. We could calculate our complex power, and then the real part of that would be our average power that we're looking for. That's one way. I'm not saying that that's a wrong way by any stretch of the imagination, but there might be a little bit easier way. And so I'm going to scroll back up to our relationship for power factor. So we're looking for effectively the average electrical power that is supplied to this system. So to me, that looks like, if I rearrange that power factor relationship, it would be our apparent power multiplied by our power factor, where we know what our power factor is. Anybody remember what apparent power is?
That is V times I conjugate. Or V, or the magnitude of V squared over Z conjugate.
So those are complex powers.
That is complex.
I want the magnitude. So apparent power is just magnitude of the voltage times the magnitude of the current, and we already know both of those things. So what was suggested isn't wrong, but it's actually more difficult of a calculation than what we already have available to us. So I would say that the easiest way for us to calculate our in power would be the magnitude of our voltage V1, which is given to us in the problem statement, essentially. The magnitude of our current I1 that we determined in a previous step, times the power factor at which our motor is operating. So that would be 277 volts RMS times that 44.214 amps RMS. Times our power factor of 0.820. And when I put all of those in, I wound up getting 30.128 kilowatts. Let me double check that since you sounded incredulous. Oh, so let me fix that very slightly here. I forgot a factor of 3, my apologies, because this is a 3-phase machine. So I took my answer and I multiplied it by a factor of 3. There we go. My apologies for missing that 3. That was an important thing, right? So V1 times I1 is the apparent power, or the magnitude of V1 times the magnitude of I1 is just would be the apparent power absorbed by one phase, but this is a three-phase machine. So thank you for your incredulous thing, because that led me to forgetting my factor of 3 there, or realizing that I had forgotten a factor of 3. So thank you for that, Zach. All right, so our rotational losses were given to us, 1,850 watts, right? So we know what that guy is. So let's start putting things in here. So we would have 30.128 kilowatts minus 1.85 kilowatts. Now we need to figure out our copper losses in the rotor. Anybody have any thoughts on how we might do this? Excuse me, copper losses in the stator. So I want to go back to our circuit. I'm trying to find the average power absorbed by that resistor. The power of that resistor. So how do I calculate that? I squared R. And then 3 of those, because there are 3 phases. So it's literally just going to be 3 times the magnitude of I1 squared times R1. So that would be, throw that 3 out front, 3 times 44.214 amps RMS squared. R1 was 0.322. And let me just double check here. I got 1,888.411, and I will round that to, how did I get a different number there? Oh well. 1.888 kilowatts. And then lastly, I need my copper losses in my rotor. So it wouldn't just be R2, it would be R2 over S, because it's going to be dependent. Oh, no. I think it would actually just be that R2, yeah. But also you could just do slip times your air gap power as well. So what was suggested was 3 I2 squared R2 prime, which should be this exact same thing as S times PAG, which I'm going to do that second one because it's easier and I'm lazy. So that would be 0.03 times our air gap power of 28.225 kilowatts. Which I get to be 0.847. My air gap power is already taking into account that it is for all 3 phases. That's why there's this factor of 3 on the front block. So putting that in, so 30.128 minus 1.85 minus 1.888 minus 0.847 comes out to be 25.543. Underline right there. So just as a sanity check, that number should always be a little bit smaller than the mechanical power, because we're also taking into account our losses from friction and windage, secondary or rotor copper losses, things like that. So if you wind up getting a shaft power that is greater than your mechanical power, you have forgotten something or you have made a miscalculation.
Air gap.
It should also be less than the air gap power, yes. So the air gap power should be smaller than the input power, but larger than the mechanical power and larger than the shaft power based on our power flow diagram. Yeah. So the power is getting smaller from left to right in that diagram that we drew at the beginning of the previous class. Okay, so any questions about any of those calculations? All right, so what will our motor efficiency be?
Like P shaft, over, no wait, yeah.
Yeah.
P shaft over P.
Exactly right. So because our output is the power delivered to our shaft, and the input is the electrical power into our system. And I'm going to multiply this by 100% so that we have it as a percentage, just because that's my preference. So that would be 25.543 kilowatts divided by 30.128 kilowatts. And that comes out to be 84.782%. Actually, let me times 100% comes out to be 84.782% efficient. So a relatively high efficiency, which is one of the reasons why induction motors are used so much. All right. So closing in on the home stretch here. Let's figure out I. So one thing that I could possibly ask you that I am not asking you in this giant thing of example parts, but we could actually figure it out rather easily if we wanted to. So I'm about to ask you about the starting torque, the slip at which maximum torque is developed, the speed at which maximum torque is developed, and then what the maximum torque is. But I could have just asked you about what torque is being generated at this particular slip as well. For what it's worth, that would literally just be the air gap power that we found divided by omega S, right? Where omega S would have been 2 pi times 60 hertz for us. So not doing that one. Don't know why I didn't include that in here. I guess maybe I felt like 13 parts was unlucky when I wrote this problem out last year. But anyway, that's another thing that I could potentially ask you. Fairly straightforward deal, and you just have a direct equation for it. So anyway, so the starting torque of the motor, T start. So this is one of the equations that that I introduced today, right? So it would require us to do so omega S is, huh?
We have everything filed there.
Right. So omega S is just going to be, so I have an equation here, just to be clear. NS is multiplied by 2 pi over 60 hertz. But this is going to be the exact same thing for what it's worth as just 2 pi times Fs, 100% of the time. Okay. So this would be 120 pi radians per second, or if you don't like having it expressed in pi radians, 376.991 radians per second. For what it's worth, if you ever are in industry or anything like that, or maybe Ron might have used this when you guys were in your version of Circuits 1 and all that kind of stuff. But if you're ever talking about a system that is operating at 377 radians per second, that's a 60 hertz system. We would just round that 376.991 up to 377. So that's a fairly standard approximation that's made throughout industry. 377 radians per second is the same thing as a 60 hertz system. Okay, anyway. So there's our omega S, it's just 2 pi times F of S, or we could have gotten it by using our synchronous speed and manipulating that. Either way, we get the same result. I'm lazy, 2 pi F is the way that I would prefer to do it. Now that we know what omega S is, our mechanical starting torque, so T start is going to be 3 times our Thevenin voltage squared times R2 prime. That is not R2 prime over S because, as Zach correctly indicated earlier, at startup, our slip is 100%. So that's why we don't have an R2 over S, because R2 over 1 is just R2. Then we would have our omega S term, and then we have that R Thev plus R2 prime, all of that squared, plus X Thev plus X2 prime, all of that squared. Close my square brackets, substituting in my numbers here. That's going to look like 3 times 262.808 volts RMS, quantity squared, 0.196 ohms. $376.991 radians per second. 0.290 ohms plus 0.196 ohms. Square that guy. 0.675 plus 0.510. Square that guy. Close the bracket. And this comes out to be 65.670 Newton meters. So just to be really, really clear where those units are coming from, A Newton meter is the same thing as a joule. That's just energy, right? So we have voltage squared divided by resistance, because we have a resistance squared in the denominator, right? So what's voltage squared, what's V squared over R? What is that a measure of? So power in watts. But then we also have this 1 over omega, so that's going to give us 1 over seconds, so it's watts times seconds, which is a joule. So there doesn't need to be any conversion factors. This is going to come out to be in the same thing as a joule, which is the same thing as a Newton meter. So you don't have to add conversion factors and all of that kind of stuff. I just wanted to make sure that you guys were aware of that, since this is our first time doing the calculation. There is no need to do any unit conversion here. So that's our starting torque, 65.670. Now let's look at, I'm assuming there were no questions about that direct application of that equation. Now let's find the slip at which max torque occurs. So this is something that was given to you guys earlier today in class. Didn't really derive it, just told you how it was derived. So this was R2 prime over the square root of R Thevenin squared plus X Thev plus X2 prime, quantity squared. I'm hesitating here. Let me scroll back up. Yeah, I'm going to need to. I'm going to need to double check something. So we're going to leave the equation as is, but I might come back to you guys and tell you something different. So my concern here, and I didn't notice it a couple of moments ago, or until just a couple of moments ago, is that I have a minus sign right there, and I have a plus sign right here. And to get from this relationship to this relationship is literally just reorganizing things ever so slightly. So there shouldn't be any reason for that sign right there to change. I feel pretty strongly that it actually should be a minus sign, but because I'm not 100%, I'm going to leave it as is. I'll look that up, and then I'll probably send you guys an email to tell you, hey, it should specifically be this, because I don't have the textbooks or anything with me. So we'll leave it as is, but just know that there might be a minor mistake right here based on that one particular sign. So if I plug in my numbers here, going with things as they are, that would be 0.196 ohms divided by the square root of 0.290 ohms squared plus X Thev was just X1, 0.675, thank you for that. And then X2 prime is 0.510. And I wound up getting 0.161, or a slip of 16.066%. And again, I'm gonna put an asterisk here just in case I got that sign incorrect. I do, but I have it in my notes as positive, and I just want to leave it as what I have in the notes. It's all positives? Okay, so I might have had it. So maybe this guy right here was supposed to be positive then. Okay, that's fine. I'll double check it just to make sure, but a quick Google seems to have bared out that the positive sign was the correct thing there. Anyway. What?
Still don't count.
I don't, so for what it's worth, the reason why I don't feel confident in that is because when you're finding the maximum average power delivered in an electrical system, it does have a minus sign. But I understand that this is a different animal, and so that's why I'm okay with it being a positive sign, but I want to do the research myself just to make sure. That's all it is. It's just, I have too much random things rattling around in my brain that I feel should have some sort of parity, but I'm not 100% sure that they actually should. And I genuinely don't want to tell you guys definitively and then be incorrect. So I'm hedging my bets to give myself time to look it up and come back with to it in our next class meeting. All right, so part K, we're almost done. So this is a fairly easy calculation. I want us to know the rotor speed at maximum torque development. So effectively, how fast is our rotor spinning at max torque? So anybody have any thoughts on how we might calculate that, since this is something that we don't technically have an equation for, we just know enough to be able to figure it out. So we know our slip. So how did we calculate our rotor speed at a slip of 3%? NS times 1 minus the slip. So we're just going to do the same thing here. We're just going to use the slip where max torque was generated. So that would be 3,600 RPM, 1 minus 0.161. And this came out to be 3,020.4 RPM. And then the last thing would be our maximum torque developed. So this is just direct application of one of the equations that I introduced today. So that would be 3 times the magnitude of the Thevenin voltage squared divided by twice omega s multiplied by R Thev plus the square root of R Thev squared plus X Thev plus X2 prime squared. So 3 times 262.808 volts RMS, quantity squared. And then I would have 2 times 376.991 radians per second. 0.290 ohms plus the square root of 0.290 ohms squared plus 0.675 ohms plus 0.510 ohms. Square that guy. Close my square bracket. And I wind up getting 181.999, so 182 Newton meters. So as I mentioned previously, I would be hard pressed to literally think of anything else to be able to ask you guys, other than just calculating the torque at a given slip, which would use that relationship right there. I think that's the only one that, literally the only equation that I've given you that we didn't use in that one problem.
What was the inch? You just add it to, or make another part, just so we can do it.
Sure.
0.837.
So
And
L, so let's say M. Okay, so the torque developed at a slip of S is equal to 5%. Sure.
I got a different answer. For that.
What did you get, Zach?
Like, 181. Oh, no. Yeah, I got 320. 0.02.
I could have calculated it wrong. Let's see. So 3 times 262.808 squared. Down here, I have 2 times 376.991. (0.290) plus the square root of 0.290 squared plus worried about my calculator giving a math error. What's 0.675 plus 0.510? I should be able to do that in my head, but I don't trust myself right now. I feel like it's 1.185. Don't give me a math error and be a dick. Nope, I got 181.999. All right, so torque at this particular slip. So two ways to approach this. The reason why I chose a slip that isn't 3% is just so that I could illustrate something here. So if I had done the torque at 3% slip, if we go back up here, it would literally just be the air gap power that we found previously divided by omega S, okay? But because we have a different value of slip, our air gap power is now going to be a different thing. So instead, I'm just going to use this equation directly, which takes into account the value of the slip itself, okay? So that would look, scrolling all the way back down here.
An extra 0.
So I'm explicitly doing it in this new part M that Nick requested for a slip of 5%, just so that we can have an example of this calculation, okay? So T mech, I think, yeah, is going to be, let me get those notes. 3 times the magnitude of the Thevenin voltage squared R2 prime over S omega S times,
Can we just do? Or you can even step up. Can we just do power of the air gap over omega n?
so the power of the air gap over omega S would be valid if our slip was 3%, because we calculated that air gap power at a slip of 3%. But because I'm choosing to give you guys a different slip percentage, we can't just use that air gap power because air gap power is dependent on the slip. Okay, so this would be our relationship. Now we would plug in our numbers. Let me scroll back here. I just want to make 100% sure. I'm 99% sure that the value of our Thevenin voltage and the value of those Thevenin impedances are not dependent on slip. I just want to double check to make sure we don't need to recalculate any of those. So Thevenin voltage, nowhere do I see an S. R Thevenin, nowhere do I see an S. X Thevenin, nowhere do I see an S. So we should be good to go on all of those quantities. For what it's worth, it should make sense that none of those things depend on slip, because all of those were stator related quantities, right? So that was the stator winding, the stator reactance, and the core reactance, everything having to do with the rotor and therefore slip was not taken into account when we found that Thevenin equivalent circuit. Just wanted to make 100% sure on that. So this would be 3 times, I believe, 262.808 volts RMS squared. Then we would have 0.196 ohms over 0.05 in this case. Our omega S is 376.991 radians per second. R Thev was 0.290 ohms. Then we'd have plus 0.196 over 0.05. Square that whole thing. X Thev was 0.675. X2 prime was 0.510. Square that. Close brackets. Give me 3 minutes to throw all of this crap into my calculator. So that's my numerator, shift store A. Then I have 112.636 Newton meters. So I have a thought on a question that I would like to ask you guys on your take-home portion of this exam. But I'm trying to decide whether or not you guys would be furious, so I'm just going to ask you flat out. So something that's interesting, we can see from this particular problem that our, so at a slip of 5%, our torque was 112.636. At a slip of 16%, our torque was 181.999 newtons per meters. At a slip of 100%, our torque was 65.670 newton meters. Would you guys be wildly opposed to me having you use Excel or something like that to generate a graph of slip, or excuse me, torque as a function of slip over a particular range?
So it would be just the same equation, just changing the
The slip is the only thing that's going to change, so that's your only variable, so everything else is literally a constant.
I don't think that'd be too bad.
Okay, then I'm gonna have you guys do that as part of one of your take-home exam problems, is throw it into Excel and see what it looks like. Yeah.
Using Excel.
Yeah, I just want to make sure I'm not being too much of an ass. Okay,
Oh, no.
I can't hear you over this. Yeah,
That one, that program, that
Best programs that I've been using for years and
Okay.
years.
all right. So on Thursday's class, we are gonna start talking about synchronous machines. That is not going to be on the upcoming test. The test material stopped with today. This is a reminder, you've got a homework due tomorrow, a homework due Friday, and then also a homework due the following Tuesday. All told, that is 7 problems. Okay, so
And one of those, is, the one we just, the sharp one that you were talking about earlier.
yeah, that you could literally knock out in seconds. All right, thank you guys.